penultimate speaker will be Gregory, once again, talking about verification of C++ programs.
The themes of my talk might suggest this is the only thing I do. It's not, but it's one thing I've done for a while now. So in this talk, I'm going to talk about verification of templated code in C++. We saw a talk by Bloomberg this morning, and there was a slide that had a lot of templates on it. And so clearly, templates are something that are used frequently. And just to make this talk self-contained, I've done a lot of verification of C++ code in this hypervisor stack, which we've seen before. Mainstream C++ uses this crazy standard library, which we saw in the last talk. And one interesting thing about the standard library is not only does it have recursive mutexes, but it also has heavy use of templates. And I would claim that, like, while we often think of C++ like was originally thought of as, okay, this is C plus classes, I would say that in many cases, modern uses of C++ is really like C plus templates. Okay, so a lot of the work that's gone on in C++ recently, I feel like, has been pushing templates even farther and kind of almost de-emphasizing, maybe to some extent, classes and virtual dispatch. So in this part, I'm going to talk about, so we talked about brick, and you haven't really seen it, but it's a program logic for C++. And in this part, I'm going to talk about how can we take this brick program logic, which is about runtime C++, things that actually run, and kind of glue on template verification. Templates do not run. They're compile time expanded. So let's talk a little bit about how this works. And I'm going to say this, if you are one of these people who doesn't care at all about C++, but you do care about macros, everything in this talk, or almost everything in this talk, will also apply to you. So here's a very simple templated piece of code. This inc twice function is something that no one would ever write in practice, but is small enough to fit on this slide and demonstrate a few interesting concepts. So inc twice is this function. It's templated over a type T. You might think of this as polymorphism. And it increments x, and then it increments the result of incrementing x. And we can call that function twice, inc twice x at type int, and inc twice c at type c. And in this case, it will use the primitive integer increment. And in this case, it will use this overloaded operator ++, which you can do in C++. So right now, we can verify this code. Everything that would actually run in that test main function down there, we can verify. And we just do it like this. We say we're going to verify this function. We write verify spec. And then actually, the proof of this function is just go. It's literally 3 characters that would have been shorter than writing the comment there, because we have reasonable automation. But we still have to duplicate the proof. And this won't scale if we're thinking about doing something more interesting, like, you know, vectors or things with loops, where we might actually have to write a specification of a loop invariant, for example. So what we're aiming for is a proof of inc twice, not a specialization of inc twice, just a verification of inc twice, to verify that templated code and then to apply it here. And we want to make sure that this strategy does not enlarge the TCB in any way. So we don't want to have to deal with overload resolution or other problems, and we don't want to add those to our TCB in any way. Okay, so there's a lot of things we had to do. Some of them are described in the paper somewhat tersely due to the page limitations. But in this talk, I'm going to focus exclusively on the question of how do we actually specify templated code. And that looks roughly like this. So here I'm writing a specification for kind of an arbitrary piece of code. One thing to note is we're going to use standard brick syntax for function spec. So this is, it takes an argument that happens to be a reference to the value t. And then we're going to use regular Rock level quantification, a section in this case, to quantify over the representation predicate that represents the ownership of the value of that type. And in this case, I'm just keeping it very simple and deciding that when you call the inc twice function, the representation predicate, the abstract representation predicate that is going to use is going to be a predicate over z's, some numbers. We quantify over explicit substitutions here. So that's going to allow us to not have to think about the whole program, because overload resolution is something that looks at your entire program, and we don't want to have to think about, working with this every time things change. So you can think of this as the minimal piece of the substitution that's actually necessary to instantiate this function. And the statement, instead of being a statement about the function, it's going to just be a statement about the body of the function, because every time you instantiate a function, it gets a new name. It gets, in particular, inc twice of int is a different name than inc twice. And the last thing, and the thing where I'll spend most of my time on here, is about instantiation constraints. So we'll need a way to specify what happens when you say plus plus of x if you don't know what plus plus is doing. And this is the way we'll do that. And for most of you, you'll say, well, it's kind of like a function, so let's just specify it as a function and get on with our lives. It's a little bit more complicated than that, and that's what we'll talk about. But if we set things up in this way, then everything's ROC level quantification, so we can just apply this in basically the same way that we saw before and then discharge that obligation. So we'll walk through what exactly that obligation says. Okay, so let's take a look at operator plus plus of x and see how this might work. So what happens, what does C++ do? So when it looks at any particular instantiation like this one or this one, it will figure out the type of x, and elaboration or instantiation goes bottom up. Type checking goes bottom up. So it says, okay, I've got operator plus plus applied to int ampersand. What does this do? Well, in C++, that's implemented by primitive pre-increment. It's a primitive of the language. For the class C, this is an overloaded member function, so we'll call that. But this is just the regular overload resolution. There's nothing template specific inside of here. Things get a little more complicated because when we use this in another context, the lookup now that has to happen is not a lookup on necessarily t ampersand. It's a lookup on whatever type was returned when you called plus plus x. In some cases, this would not be valid code. For example, if you instantiated t with atomic int, it just turns out that the library does not quite do what, in my opinion, is the right thing there, but so it won't quite work. But it turns out that, so in both of these cases, for int and for C, the return type of plus plus x happens to be the same as the input type. And we can characterize that in our specification by giving a concrete kind of statement. It says the return type of this expression, of an expression of this form, is going to be this value. And the nice thing about being able to do this is that we now know that both of those plus plus operators refer to the same term. Okay, they're both going to be resolved in the same way because the value of x here is t ampersand, and that constraint that I just showed you is saying that the type of this plus plus x is also t ampersand. Okay. And if I couldn't do this, I'd have to give you a specification for not only operator plus plus applied to t ampersand, but also operator plus plus applied to the declaration type of plus plus x, which would be kind of annoying. Okay, so now we're going to focus on this box, which is really about the functional verification portion of this. And to do it, to highlight the kind of subtlety here, we're going to look at a slightly different example. Operator plus, which now takes two arguments. So here, t ampersand and t ampersand are my arguments here. And so we look here at add, operator plus, taking two int ampersands. This operator doesn't actually exist in C++, but there is an implicit coercion called the left to right conversion that will take an int ampersand and return a value of type int. Okay, so that's this EL2R. And then we can plus those two things. So this is what the code that Clang will generate kind of is the intermediate format here. And the interesting thing about this is that when you run this value here, when you run this program, the semantics says you can non-deterministically choose to evaluate this argument first or this argument first. But when you do it, you have to evaluate the whole argument. So you will evaluate like E1, and then this left to right cast, and then E2, and then this left to right cast, and then the whole thing. So what you have to do is you are evaluating, you're intermingling code that comes from the context with code that comes from the holes that get spliced into this context. So to capture that, we use predicate transformers, and now I'm switching back to the pre-increment thing. So apologies for the slight back and forth here. But here you can see what we've got as a lambda that's taking E. This is going to be the weakest precondition, a predicate transformer, for the evaluation of the first argument, the only argument in this case. And then Q is going to be the continuation, what to do afterwards. So this is written in basically a weakest precondition style, and it says you're going to take the value, you're going to have ownership of R at value V, and you'll return ownership of R at value V plus 1, and then continue with Q by returning P. So I said all that. All right. And so then we can nicely, take this, we can verify, we can prove this theorem. I haven't showed you how exactly we do it. It's a little bit interesting, but for people familiar with these sorts of program logics, probably not too surprising. And then we can use it to discharge proofs like this. All right, so that's it. Again, Brick program logic and automation are online, and if you're interested in this sort of stuff, happy to talk more about it.
Questions?
Thanks, Ralph.
Yeah, thanks, Gregory, for the nice talk. Nice to see that someone is finally daring to tackle the BBEG that is C++ templates. So I don't think I fully understood this connection between the non-deterministic evaluation order and then you switch to predicate transformers. I mean, as far as I'm concerned, predicate transformers, very natural way to express your specifications. But what does that have to do with argument evaluation order? And I mean, in this example now there's only one argument, so I guess there's no order anyway.
Yeah, so if you were, so the reason that I called this out is because normally you'd think about this as function arguments, right? Like, in fact, the first time we were working on this, we said, okay, you evaluate the first argument, then you evaluate the second argument, or vice versa, and then you evaluate the closure, like the context, right? That's what you naively think. But it doesn't work because there's actual interleaving between the code of the argument, f of like the L and the R. These things can be non-trivial expressions, but also the implicit cast can be non-trivial expressions as well. So if you think about this as a function where you say evaluate L and then evaluate R, you won't get a sound proof rule because you won't have accounted for the side effects that could occur in here. Does that make sense?
Okay, and so now how does the spec issue on the next page resolve that?
It's because you're kind of obligated to show how these things get sequenced. If you had multiple arguments, you'd have to say something like E is run, and this post-processing is done on it. And then E2 is run, and this post-processing is done on it. And then I combine the results. So it gives me a way to talk about all of these different pieces, the semantics of each implicit cast, plus the semantics of the whole thing.
So the let star P equals E here is some sort of weakest precondition for E?
Sorry, it's meant to be monadic bind, basically, yeah, of a WP.
Ah, okay.
Yeah, sorry.
Yes, okay, that makes everything a lot more clear, thanks.
Yeah.
I wonder, normally in this sort of templates, you have kind of a lot of compile-time computations, right? Does your frontend already compute those and you see the computation results, or do you somehow reason about the results of the computations that happen at the template instantiation time?
I'm sorry, I did not quite understand.
If you have some computation in your template instantiation,
yeah,
does the frontend already handles that and you see all the results, so you don't need to reason about those, or is there some sort of reasoning you do or you plan to do?
You're saying like if I have function foo applied to angle brackets 1 plus 1.
Yes, for example.
We see the evaluation of 1 plus 1. No.
We have time for one more question if there are any. If not, let's thank Gregory one last time.
Thank you, guys.